This is the 3-axis demo and the parts comprised with it when it is shipped to you. A base plate, 3 L70 actuators, a Z-axis, X, and Y-axis, labeled as motor 1, motor 2, and motor 3. 2 Motor daisy chain cables, 1 smart box demo, 1 ink pen holder to go on the Y-axis, a CBL SM1- demo, it's RS-232, and communications and power, and then of course the power supply, which is a 24 volt 5 amp laptop style power supply with its AC power cord. Okay, I'll show you how to put this together. Take the one that's called the Z-axis motor 1, place this on the dovetail slide that's on the base plate. When you look at it, you'll see one long edge sticking out. That will go up and away from the center of the base plate. Basically, slide that on and in place. I'm not throwing the pins in here that hold in place, but this will work. The next axis is the X-axis, the axis 2. Dovetail slide here. You need to slide this in on the back side of motor 1. Okay, then the Y-axis demo goes on top of there. You have Z-axis, X, and Y-axis. Also, you have the ink pen holder. And I'll put some paper in here in a minute. Okay, I've added the paper to it. That will be used later. Let's go ahead and try to plug this together and make it work. Okay, take your Motor daisy chain cables. Each of them have a single connector on one end and a double backed connector on the other end. I'm going to go in reverse order. Take this single axis cable connector and place it on the final motor, the Y-axis motor. Take the double-ended connector, plug it on the next motor up, which would be the X-axis motor. Okay? Take the other Motor daisy chain cable, place the single connector on the X-axis double-ended connector that you just finished with, and then place this on the Z-axis. Double-ended connector on the Z-axis. So double-ended connector to single-ended, double-ended connector to single-ended. At this point, you take your CBL SM1- demo cable. This is going to supply power and communications. You plug that into here. That's where RS-232 will plug in. Then you take your DC power supply and you plug it into a small jack on the side. That is the entirety of plugging in and making it functionable other than plugging in AC power. Also, there's a smart box that can come with this. You don't necessarily need to use this if you're just testing, but that smart box demo will plug in to axis 1, the Z-axis. At this point, we will be ready to download and play with the program that's in the motor. I managed to find the pins that hold this together. Small little stainless steel pop-in pins. You can plug them into each axis back here and an extra hole that you see up top, or one of them in the back corner for the Z-axis. Do not put one in on the ink pen holder. It's made to have gravity hold it down. Okay, the program that needs to be downloaded should be emailed. It will be on the website. In this case, it's Class 5, 3-axis Spiro Rev 10.4. You can't quite see that at the top of the program here, but that's what it is. If you right-click anywhere in this area in your program editor screen, you can click either press F5 or right-click, click Download, and choose Global Port, Global Download to all motors. Okay, Global and Port COM10 in this case. And that will globally download to all 3 motors. Normally, I wouldn't suggest doing a global download unless you verified communications earlier, which we already did. So under that note, I will start the download. You click OK. Are you sure you want to? It'll issue End. Yes, you want to continue. Click Yes. Downloading globally to all motors. All motors will be turned off, so on and so forth. Click Yes. At this point, the status bar will come up with the progress showing the status of the download. Down at the bottom, it will say scanning the program, building the program, and downloading. Once this is done, then we'll test the program. Okay, program downloaded, finished, no errors, no warning. Look down at the bottom again to see the status of that. And what I did is I powered down and reset the motor by disconnecting the DC power supply and then reconnecting it. And I'm doing it again so you can see it again. I'm going to clear the screen so you can see what I'm talking about. Okay, I power it down. Whatever's left over, I want out of there. Power it back up, and then it should say press go to home all motors. What it's referring to is this switch here. So when I press go, it's going to call a subroutine that homes to a hard stop on all 3 axes. And you'll see it says homing axis 1, please wait, homing axis 2, please wait, and so on. Homing complete. Now it says press select to select the next demo option. Press go to run the selected demo. Okay, what that's referring to is this switch right here. If you click select, you're going to see all the options. Option 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 if I remember right. And those are all the options you can do. You click go, and whichever the last one was you saw on the screen is the one that it would do. In this case, I want to do the 2-axis random moves plotted demo. So I get it down to the number 2 option by clicking select until I see 2-axis random moves plotted, and then I click go. In this case, you'll see the motors move to center and move down to the bottom. The reason I want you to do this one first is I want you to adjust the ink pen to sit on the paper. What you do is you lift it up, push the ink pen down until it's just touching the paper and gravity is holding against it while it's in that dovetail slide. At this point, you can click go and it should run that demo. And in this case, it's going to run some random 3-axis demo or 2-axis demo moves, and you'll just see some random places, linear interpolated. By the way, the potentiometer will adjust speed. If you slow it down, it'll go slower. If you speed it up, it'll go faster. Okay, after running that demo, you can see random moves all over the place. Okay, that's just the 2-axis. The 3-axis demo is the same thing, but it's up in the air. It's just harder to see. So what I'm going to do is take that piece of paper, flip it over, and I'm going to run one of those Spirograph demos just so you can see it. Now, keeping in mind, motor 1 is the master axis. It's telling the other motors to do different things. So I'm going to click select. I cleared the screen a little bit. You'll see Spirograph plot 1, 2, and 3. It's left over from where I cleared the screen. Dynamic calculated or whatever. So what I'm going to do is go back around to the first Spirograph plot, number 3, and it says Spirograph plot 1, and then click go. What it's going to do is move off of there a little bit, move back down. It's going to write out a pre-scaled cam profile and start drawing that profile on the paper. Now it's going kind of slow, but this is a 360 point cam table that it's actually doing the calculations ahead of time, pre-scaling, and then running the cam. And you'll be able to see that it's a circular pattern, and the reason it's called Spiro Demo is it's from the old Spirograph plastic toy. Okay, it's just a couple of sine and cosine functions and so on. Okay, it completed that plot just now, and you can see it does look like one of those Spirograph drawings from years ago. Now I want to reiterate what's happening here. The same program is in all 3 motors. Axis 1, or the Z-axis, basically pre-calculated the cam values and then told motor 2 and 3, X and Y axis, to run the cam profile. And that's what this turned into. And just to be sure you understand this, in no way did SMI, the software on the screen, have anything to do with how the motors were running. Everything is self-contained within the motors. The only thing SMI is a window into the program. So when I click select, I'm actually taking an input value into motor Z and looking at the next menu option. Spirograph plot 2, dynamic calculated 1, dynamic calculated 2, and so on. So all of this is inside the motor. I have a palletizing 3x3 matrix. That's a typical pick and place point-to-point type thing. If I click on that one and click go, the motor has all the data in it. And in this case, it's going to go down to a pick location and act like it's picking up and then moving over to a place and then back to the pick. In this case, it's a 3x3 matrix. So you have 1 pick location, 3 up and down, left and right place locations. Simple palletizing program. This is utilizing the PTS command functions. Okay, PTS means position target synchronized. So it is synchronizing motions between the X, Y, and Z axis, mostly X and Y in this case. Z axis is just a down and up. So in this case, the down up portion is a sub function in a subroutine that just says, okay, I've gotten to where I'm going, now go down and come back up. Okay, there again, everything resides inside these motors. There's nothing from Windows operating system that's doing anything at all right now. Okay, so it's gone through the pick and place until it finishes it, or you can click select to get out of there because I put an exit in that part of the program. Okay, now that we're done with the palletizing demo, I want to click select through to the next one. It says puppy. Well, what is puppy? Okay, I took a CAD drawing of a puppy dog, and I put it through our CAM import engine in our SMI software. If you go up to the menu option here, there's tools and import CAM table. I don't want to get into the details on that. You can call us up and contact us on the phone. The bottom line is I imported CAM data points from this drawing of a puppy into the motor, and then I'm going to have it run it. Okay, so I'll go ahead and click go so you can see what this looks like. And it says writing CAM tables. Well, this is a long CAM table. So now it's moving just above the paper, and I got to make sure the ink pen is where it's drawing. Okay, and it's going to start drawing out this puppy dog. Now this takes a minute, so I'm not going to show that for the entire video. But the bottom line is it's a downloaded CAM profile that was imported from a CAD drawing. Okay, it finished the puppy dog, and as you can see, it looks like a puppy dog. Now, one thing I want to talk about is the Spirograph Demo was a math formula. The puppy dog was actually an import from a CAD drawing. There's a slight difference in how they ran. In both cases, though, they were pre-calculated and then run. So what I want to do now is go through here and select until I get to one that says, let's say number 5, Dynamic Calculated Number 1 Demo. The reason I want to show you this is we have two ways of running electronic camming. One of them is pre-calculated and the other one is running on the fly. So I'm going to go ahead and select that and click go. It's going to move to center, move down, and start plotting this pattern that's literally mathematically calculated dynamically. So it isn't a pre-run CAM table at all. It's not from a CAD file. It's nothing like that. It's literally a math formula and calculating the data on the fly. Now, the reason I want you to see this one is it's not a typical way that most motion controllers operate. Now, how it runs in CAM mode, I actually have the clocks synchronized. It's telling it to run these starting from time 0, so they're synchronized through CAN bus, updating the clocks between the motors. Since it's a separate CAM table in X and Y, I had to do something to synchronize to make sure everything's right. That also applied to these two. The difference is that the Spirograph and the puppy dog, they were pre-calculated. This one's actually doing the math function while operating. Okay, the dynamically calculated one is just completed. You can see it's pretty decent looking little drawing. Not much fancy about it other than it is a math function that was running dynamically. Now, to talk about that a little bit more, two ways to run things, either preset values or dynamically calculated, typically within the smart motors, and this is all standalone. You can also just send data from a COM port, either RS-232, 485, or even CAN open, or in our Ethernet products over Ethernet. Honestly, for small, simple machines, Ethernet it isn't worth the cost effectiveness to go to an Ethernet protocol. If you're less than 10 axes, it doesn't really make any sense to do that. You're not gaining anything. Okay, so we went through quite a few of the demos, dynamic calculated, palletizing, the puppy. I didn't do circulation and interpolation demo. It's just basically drawing circles. CAN bus gearing demo might come in a little bit handy. I'm just going to show that one real quick. CAN bus demo is a little bit different. It moves everything to center of axes, and then basically motor 1 follows an external encoder. So when I move axis 1, it moves up and down. Motor 2 and 3 are actually electronically geared over can open from motor 1. So motor 1 is looking at this external encoder to move up and down. Motor 2 and 3 are following motor 1 position data packets over CAN bus. Okay, as a result, all 3 axes are moving. So in this demo, you have seen position mode, you've seen camming, you've seen gearing over can open, you've seen a couple of different kinds of CAN bus, or excuse me, electronic camming. All of these are connected over can open. These are the CDS7 motors, so this one cable actually has RS-232 power and can open going between it. The can open protocol we're using is the standard CIA 402 motion spec, as well as our Combitronic, and they both protocols coexist on the same cable. The last thing I want to show you is the C20 subroutine in this demo program. C20 is what's being called anytime you do an X, Y, and a Z move. The good part about this is it's already pre-written. We have 3 axes here. All I have to do is set the value of X, Y, and Z, call the subroutine, and they'll move there. Left over from a prior demo that was doing the electronic gearing, so everything's at center stroke of the axes. So we're on the same page, if you type 1 RPA, 1 report position actual, it's roughly 40,000. 2 RPA, 46,000. 3 RPA, roughly 46,000. So they're all within a few counts of 46,000, which is center stroke. If you set the variables X, Y, and Z to some value between 0 and 90,000, you can go there. So basically what I'm going to do is say motor 1, I want to talk to it, so I'm just going to type 1 RPA. Motor 1 is the master motor. I'll just say, let's say X equals 1, 2, 3, 4, 5, I don't know. Y equals 30,000, okay? Z equals, I don't know, 50,000, okay? And then I type go sub 20. And by the way, this is all uppercase. GOSUB in parentheses 20. Hit the enter key, and it should go to those positions, okay? Let's just see if it did. 1 RPA. Well, that's within a few counts. You got a brake motor there, so it's 50,009 counts. 2 RPA, 1, 2, 3, 4, 5. 3 RPA, 30,000. So it went exactly where you told it to go. Now, if you noticed, I happen to double click on a line up higher just so I can resend the same command. Otherwise, you can type it in. So that one subroutine, C20, is how you would do an interpolation protocol type move using our PTS command functions. So that pretty much concludes the overview of this 3-axis demo. Feel free to contact us at animatics.com or our phone number that's on the website, and we can discuss more things you can do with these motors. This demo is available for all distributors to help with customers and key account customers who want to understand more about the smart motors. There again, feel free to contact us with more information. Thanks.